All right, so our last lesson in this chapter is going to look at applications of the dot and cross product. And those applications are going to be in physics because we use vectors a lot in physics. First, work. Now, work in physics doesn't mean the same thing it means in English, right? What it is the amount of energy that is added or removed from a system. Okay, so for example, if this person is pulling this cart, then the cart goes faster because he's applying a force over, so he's applying a force over some displacement, which then we say does work on the system and adds energy to that system. So work has the same units as energy, which is the joule. And we can calculate work with the dot product between force and displacement. Okay, so if you look at this question, we have a force applied at some angle of 30 degrees above the horizontal, and our displacement is of course across the horizontal because we're pulling this cart along the surface. In this case, they say 30 meters. So you can almost look at the dot product like you're finding the scalar projection of the force, or the component of force which is in the same direction as displacement, and then we multiply those two values. Next, if we're looking at the cross product, an example is torque. Now torque, I'm sure you've opened a door before, so when you open a door, you tend to apply the force furthest away from the hinges. It's a lot harder to open the door if you try to open it very close to the hinges. Now a torque is a force which causes rotation. Okay, the rotation of an object around some sort of rotational axis. Okay, and although they have similar units, I mean, work is Newton meters, which then we call joules for energy. This is also Newton meters, which is the force that you apply multiplied by the distance from that rotational axis. So the greater R is, the greater the torque. Now I should actually mention that we should change this around, because it would actually be R cross F if we're properly trying to figure out what the direction of torque actually is. And you can use the right-hand rule that we learned before. This is another kind of right-hand rule. It's just the same thing, really. So what you do is you take all your fingers and you put all your fingers in the direction of R, which is the position vector, right? And you rotate them towards the force. And then your thumb points in the direction of force. It's no different than when we did this one. So your index finger would be R, your middle finger would be the force, and your thumb would point in the direction of torque. Notice that in this direction, the direction of torque is actually into the screen or into the piece of paper if you're looking at the handout. Okay, so those are the two examples that we're going to go over for the dot product and for torque for our cross product. And we'll do some examples, but before we do that, I want to sort of expand on what we did yesterday. So yesterday we used the cross product to determine the area of a parallelogram. Well, now we have a parallelepiped and we want to determine the volume. So we know that the area of the base, if we have this vector here, C, and this vector here, B, the area of the base is just the magnitude of their cross products. Now if you wanted the volume of the parallelepiped, we just need to take the area of the base and multiply by the height. Now here we have this vector A and an angle, let's call this alpha, to the vertical. So we can just use a simple trig ratio, the cosine ratio, to determine that the height is just the magnitude of that hypotenuse A times the cos of alpha. And then the volume of our parallelepiped is the area of the base, which is the magnitude of a cross product, times the magnitude of A times cos theta. And this looks very much like the dot product. So it's the dot product between A and the cross product of B and C. And you want to make sure you do the cross product first, not the dot product. Because if you do the dot product first, you're going to end up with a scalar, and you can't have a scalar in a cross product. Okay, you can't do scalar cross a vector. Okay, so you do B cross C first, then you'll take its dot product, and you want the magnitude of that. All right, so let's go over some of our examples then. Our first one is work. So in work, here we have Mariana is pulling her daughter in a toboggan and exerting a force of 40 newtons right here, acting at 20 degrees to the ground or to the horizontal. If Mariana pulls the child a distance of 100 meters, how much work is done? Well, let's remember that work is the dot product of force and displacement. Okay, don't worry about too much about the delta. I teach physics, so I'm used to the delta because we use d as a position vector. So delta just means change. So change in position, which is displacement. But again, don't worry too much about that. It's just force times displacement. Well, the dot product of it, sorry. All right, so force then, we're going to need the magnitude of that, which is 40 newtons. We're going to need the magnitude of displacement, which is 100 meters, and then the cos of the angle between them. So we have 40 newtons times 100 meters times the cos of 24 degrees. And that gives us the work done as 3,654 joules. Next is an example with torque. So here we have a 20 Newton force applied to the end of a wrench that is 40 centimeters in length. The force is applied at an angle of 60 degrees to the wrench. Calculate the magnitude of the torque about the point of rotation. So torque, I usually write it as this curvy T, which is called tau, and equals R cross F. Okay, and of course the magnitude of torque, because that's what they're asking for. We can use our geometric cross product, which is just R, the magnitude of R times the magnitude of F times the sine of the angle between R and F. So R is, it says 40 centimeters, but it needs to be in meters because torque is measured in Newton meters. So let's change that to 0.4 meters times by the force, which is 20 newtons, times by the sine of 60 degrees, which is √3/2. So this is going to be 0.4 times 20, which is 8, times √3/2, which is just 4√3, which is approximately equal to 6.9 Newton meters. Okay, now if you're interested in the direction of that torque, well, let's just draw this somewhere. So here we have a wrench. Something like that. That's not too bad. Okay. And it says, so 20 newtons is applied at the end of a wrench that is 40 centimeters in length. So let's say we apply a force. I'm just going to pick a direction here because it doesn't specify in the question. Let's say the force is in this direction. This is where the axis of rotation, so the wrench revolves about this point. So that is R right there. So now what you're going to do is you can take your index finger pointed along R, your middle finger pointed along F, and you'll see that the torque is into a page or screen. All right, last question. Now, this is an interesting question. So we have three vectors, u, v, and w. And first, it's asking us to find this triple scalar product, and then this triple scalar product. And then we're going to look at the significance of the results that we're getting. So let's start with the first one. So U dot V cross W. Now we have to do the cross product first, so I'm just going to put in U as 4, 3, 1. Dot, sorry, not cross. V, which is 2, 5, 6. Cross W, which is 10, minus 3, and minus 14. All right. So let's leave U where it is first, and let's figure out the cross product between V and W. Okay, so first, for our x-coordinate, we're going to have minus 70 plus 18. And I just get that by doing 5 times 14, negative 14, and then subtract 6 times negative 3, which turns into a positive with the double negative. And you can draw that helpful diagram if it helps that we learned yesterday when we did the cross product. Then we're going to have 60 plus 28 and minus 6 minus 50. And definitely confirm that for yourselves if you need to draw the diagram. So now we need to do the dot product between 4, 3, and 1, and minus 52, 88, and minus 56. So we're getting big numbers, but the answer is actually quite interesting. So first we're going to get minus 208, so 4 times negative 52, plus, so 3 times 88, so 264, and 1 times minus 56, minus 56. And those give you 0. So that's interesting. Now what I want you to do is try this again for yourself, but you're going to do W dot U cross V. Now the interesting thing is when you do that, you're also going to get 0. So what's the significance of this? The significance is that all these vectors must lie on the same plane. So W, U, and V must lie on the same plane. So let me explain what I mean by that. So imagine the screen that you're looking at is a plane, the plane of the screen, and I can draw a bunch of vectors. So let's say, I don't know, 1 is W, 1 is U, and 1 is V. Now if you take these two vectors and find a cross product, you're going to get a vector perpendicular to both of them. And it could be into the screen or out of the screen. But then when you take the dot product of that vector, let's say coming out of the screen, and this one, they're perpendicular. So the dot product will be 0. You can take the cross product of any pair of two vectors on this plane, and you'll get a vector perpendicular to the third. So the dot product will be 0. So all those vectors will lie on the same plane. Okay, and that's it for chapter 7. In class, I'll show you some demonstrations with torque and work, and it'll be fun.